with the same pathway worksheet I sent you on the WhatsApp group as well. So this one again, it's simply they're asking. Okay, I'm going to quickly draw this. They're asking to include all necessary. Draw a fully labeled diagram and two electrodes. You need to connect two electrodes. There's AU3 plus. So there's an AU3 plus and an AU electrode. AU would be uh, a solid. So it's a metal. So that is what the electrode would be made of. And the solution would contain your ions of AU3 plus. So this is the electrode. We can write the equation that's going on over here. AU3 plus might be gaining 3 electrons to form AU, or the opposite might be happening. If the reverse is happening, a lot of electrons will be produced. If the forward is happening, it's going to be positively charged. And the other electrode is a nitric acid and an NO gas electrode. Uh, and so this one is 1.5 volts. We know the voltage as well. So over here, it's 1.50 volts. The other one we're not sure of, that's a nitric acid and NO. I'm going to look for the uh, equation in the data booklet. Okay, I'm pretty sure that it's not there. So I'm going to look for nitric acid somewhere. Nitric acid and NO, there's no such equation over here. So and there's no evidence of nitric acid anywhere. Still can't see NO anywhere. So I don't. So they probably must have given the equation in the. Uh, so they probably must have given an equation somewhere. But if you look at the reagents, there's nitric acid aqueous and NO gas. Gas means the gas would be in a gas jar. So I'm going to make a gas jar, and I'm going to put in NO gas in it, and the solution is going to be nitric acid, and that nitric acid is going to be aqueous. Okay, they've already stated that it is aqueous. So nitric acid is aqueous, and there's going to be a platinum electrode in the middle. So right in the middle, there's going to be a platinum electrode, and this is going to be an electrode, and the two electrodes are going to be connected together with a voltmeter, and there's going to be a salt bridge in the middle, and you need to label the salt bridge. So the salt bridge has to be there. What we don't know is we don't know what the reaction, what's the reaction that's happening over here. Okay, I know that something is happening between nitric acid and NO. They're losing or gaining electrons, but I don't know what the actual reaction is. So they probably gave that's your fully labeled diagram. So they probably gave it over here. This is the reaction between nitric acid and NO. And there's nitric acid is H+1 and NO3 -1. So this is the reaction that's happening. And they're asking, write an analytic equation to show the spontaneous reaction that occurs when an electric current is drawn from the cell. So what's going to happen? This is 0.96 volts. And this one is 1.5 volts. Okay, I'm not sure why the second equation is over here. So we're going to try and figure out what is the reaction that's going to happen. So there was this electrode, which was 1.5 volts. It was this one, the left side one, AU3 plus 3 electrons and in equilibrium with AU. And the other one was the NO3 -1 electrode and NO gas electrode. So higher potential, this is the high E0. TK, I don't think this second reaction has anything to do with it because there was no Cl ions anywhere in the electrodes that we drew in the cell. TK, there was no mention of Cl ions. So the second reaction is probably, over here, if you look carefully, the electrodes that were given, there was no mention of Cl ions anywhere. So that means there's probably no Cl ions in the solution. So this electrode has nothing to do with it. They just gave it. Probably it's going to be used in the next part or something. This is the lower E naught. So high E naught always gains electrons, so it's going to go in the forward direction, and lower E naught always loses electrons. It's going to go in the backward direction. The number of electrons gained and lost are equal. 3 electrons gained, 3 electrons lost, so that's equal. So we're going to write the overall equation, which is going to be add up the reactants. So the reactant is Au3 plus. So that's one of the reactants. And in the other equation, the reactant is NO and 2H2O. So that's NO plus 2H2O. You can, just to be on the safe side, you can write the states. It's written as aqueous. This is gas, and this is H2O is a liquid. And the products. What are the products formed in the first reaction? That's Au solid. And in the second one, the products that are formed are NO3 minus 1 aqueous and 4H plus 1. And you're being asked to find the E naught cell. E naught cell is higher potential minus lower potential. So it's going to be 1.5 minus 0.96. And that gives you, I think, 0.54 volts. So we've figured out the equation, the reaction, and we've also figured out the E naught cell. The next thing is gold can be oxidized by a mixture of hydrochloric acid. So that second reaction, this is where the Cl lines are coming from. So he's saying gold can be oxidized by a mixture of concentrated hydrochloric acid and concentrated nitric acid, known as aqua regia. Concentrated hydrochloric acid is 12 mole per dmq, so that's really high concentration. And concentrated nitric acid is 16 mole per dmq, so that's an extremely high concentration. Explain why aqua regia is able to dissolve gold. In your answer, state and explain the effect. What effect the use of concentrated hydrochloric acid and concentrated nitric acid have on the E values of half equations 2 and 3. So let's go back. And they're asking, let me rub this off. Okay, all of it. Okay, now the previous question is complete. What he's saying is that he's saying gold can be dissolved. And we need to explain that. And the first thing is, what does he mean when gold can be dissolved? That means this reaction is happening in the backward direction. I mean, that's the only way gold can dissolve. Gold solid changes into gold ions. Okay, so this is what is meant by this, that gold can be dissolved, which means it loses electrons. And we know who loses electrons. Lower potential always loses electrons. Okay, this is what we have studied in electrochemistry. It's always the lower potential that actually loses electrons. But over here, you can see that gold actually has a very positive potential. It doesn't have a lower potential. So, which is why gold should not dissolve in normal standard conditions. These are standard electrode potentials. So, in normal conditions, if you look at the three equations, gold should not dissolve. Because it's not the lower potential. It's one of the highest potentials out of the three. So it should be gaining electrons, not losing electrons. Okay, Sara, is this clear? Is this point clear? Akib, clear? Abu Rara, is this point clear?
Yes, sir.
Yes, sir.
Achha, so but then he says that if you look over here, then he says that hydrochloric acid, concentrated hydrochloric acid, it's a very high concentration. Concentrated nitric acid, extremely high concentration. So if Cl minus 1 has a very, very high concentration, where should the equilibrium shift? If Cl minus 1, because they're saying it's 16 mole per dm, that's a very high concentration. Where should the equilibrium shift? It should
Left.
shift to the left. That means more electrons are going to be produced and it would become negative. So let me give a value. Let's say it becomes 0.5 volts. ठीक है, hypothetical value. ठीक है, it's becoming very concentrated. So equilibrium shifts to the left, more electrons are produced, the electrode becomes negatively charged. So the potential drops. I said this one over here, he's using a very concentrated nitric acid as well. So nitrate ions and H plus 1 ions are extremely concentrated. If they're extremely concentrated, the equilibrium should shift to the right. Okay, so it should shift to the right. So what's going to happen is that if the equilibrium shifts to the right, electrons are going to be consumed. And if electrons are consumed, then the potential would increase. And let's say it increases to 2 volts. Okay, just a hypothetical value. I mean, it's a hypothetical value. Okay. Abu, is it clear? Sara, is this clear? Akib, is this clear?
Yes, sir.
Yes, sir.
Okay, so remember, we did Lee-Shatler principle. If the equilibrium shifts to the left due to any changes that you make to the whole equation reaction, that means more electrons are produced and the potential drops because there are more electrons present. And if for any reason equilibrium shifts to the right, that means electrons get consumed by the ions and electrons go missing because they're getting consumed. So the potential increases, becomes more positive. Okay, so now we're going to look. Achha, what we're going to do is we're going to अच्छा ये सब हमने discuss कर लिया where the equilibrium is shifting, and I've actually so I've actually changed the values over here because the equilibrium is shifting. Now if you look carefully, this is the highest potential. That means nitrate ions are the ones that are going to gain electrons. So they're going to gain electrons, and the gold equation is the lower potential now. Okay, this is what we wanted. We wanted gold to dissolve. So because the solution was very concentrated, it became the high E naught, and high E naught always likes to gain electrons. So the equilibrium should shift in the forward direction, and the gold equation relatively became the lower potential. So it's going to go in the backward direction, and gold is going to dissolve. Not only the first one, but in the second one, that's also the lower potential. So even if you use the nitrate equation with this one over here, then even this is the lower potential, and it's going to go in the backward direction. Okay, both of them are lower, and in this case as well, gold is going to dissolve and change into AuCl4 minus 1 ions. So both cases, gold is actually dissolving. So let's go back to the question. Explain why aqua regia is able to dissolve gold. In your answer, still explain the effect of using concentrated hydrochloric acid and nitric have on E naught values of equations 2 and 3. So they've given you, it's not a very big question, it's just a 3-mark question, but they've given you many lines. So what you're going to write is that you're going to talk about you're going to quote the equations. So half equation 3, tell them that the equilibrium shifts to the right. Okay, no need to actually copy the equations. Half equation 3, equilibrium shifts to the right because nitric acid is very concentrated. So as NO3 and H plus 1 concentration increases. And the other thing is, if it increases, it shifts to the right, and the potential value increases and becomes the highest potential out of the 3. Then you're going to write about this Cl minus 1. If so, half equation 2. Okay, this is what's happening to half equation 2. Now I don't know how much detail should be added over here. It's a pretty late. I haven't actually done this question before. We're going to check the marking scheme for this as well. So equilibrium shifts to where was the equilibrium shifting for Cl minus 1? It was shifting because Cl minus 1 was very concentrated, so it was shifting backwards. So more electrons were getting produced. So equilibrium shifts to the left. And the new potential decreases. And why did it shift to the left? As Cl concentration is very high. Now, let me also check the marking scheme whether they want us to make the equation or write the equation as, I mean, did they, in your answer, state and explain the effect of using concentrated hydrochloric acid have on E values? We did that. I mean, that's pretty much exactly specifically what they're asking for. So I'm not sure if you, because we're running out of space as well. So should we make the equation? I'm going to make the equations anyways. What's going to happen is, if you take equation number 2 and 3, what would be the reaction? The higher potential gains electrons, the lower potential loses electrons. The electrons are equal, so the reaction, the net reaction is going to be add up the reactant. So we're going to do that over here. So it's going to be NO3 minus 1. I mean, this is the reactant, NO3 minus 1, 4H plus 1. And the other reactant over here is AU solid plus 4Cl minus 1. And the products are going to be over here, it's AuCl4, that's a complex ion. AuCl4 minus 1 plus the other one would be NO. And 2H2. That's one of the reactions where AU is getting dissolved. And the second one is going to be, I said the second one is probably, I mean, this 2 volts is, I've pretty much changed it because remember, changing concentration does not affect the E0 values that drastically. I mean, 0.96 to 2 volts, that's a bit too much. Although we don't have we can't use the Nernst equation over here because it's a gas involved. But I think 2 volts is kind of a bit of a stretch. These two had just slight differences in potentials. So 0.96 would increase. So let me make it slightly more realistic. Instead of 0.96, it would probably become 1.20 volts. TK potentials don't change that much. And this is 1 volt. And we discussed that it was going to decrease. So I'm going to change that to, because from 1 to 0.5, that's a huge jump. I'm just going to change it to, let's say, 0.8. But that still wouldn't affect, this is the higher potential, this is the lower potential, this gains electrons, the other one loses electrons. But in this scenario, the first equation would still probably not take part in the reaction. Why? Because even if I change the potential slightly, the first one is still the highest potential out of the 3. So we wanted gold to dissolve. So if it's the highest potential 1.5, then it's going to go in the forward direction. It's going to move in the forward direction, not in the backward direction. We wanted gold to dissolve. So it's probably these two reactions that are reacting in this AU solid is getting dissolved to form this particular complex ion. Okay, is this idea clear? Sara, Akib, Abu, is this clear?
Yes, sir.
Okay, मैंने सिर्फ ये किया है. The only
Yes,
thing
sir.
the only thing I did was that I did not change the potentials that much. So if I don't change the potentials that much, just slightly change them. 0.96, I changed it to 1.2 because the concentration was high, so the equilibrium was moving to the forward side. So I did not change it drastically. If I don't change it drastically, then the first equation would not be taking part in this dissolving process because it would be the highest potential, and highest potentials, they always gain electrons. They don't lose electrons. So the first reaction has to be taken out because that would not be involved in the process of dissolving of gold. These two would react and gold would get dissolved. So let's take it, because this is the first time I'm actually solving this question. Let's check how the answer was written for this. It's here, just 1 second quickly. Acha, so which question is this? This is question number 3. Okay, they gave us a lot of lines. So I think I've opened the, no, this is the wrong paper. It's M19 QP42. This one is, so leave it. I'll send the mark scheme answer for this later on because I think this paper number is incorrect. This is part 5. 1 second, part 5. There is no part 5. No, this paper number is wrong. चलो बाद में देखेंगे, but hopefully you got it. जो मैंने explain किया, that's how you're going to solve this. वो दोनों के ऊपर comment करोगे कि how the potentials would change, and then you're going to write this equation to be on the safe side. ठीक है, higher potential gains electrons and the lower potential actually ends up losing electrons. ठीक है, आगे is this clear?
Yes, sir.
I said next question number 4. वो मैं end में ना I'll send you the market scheme answer as well. Just let me find the question first. Now use the standard electrode potential data from the data booklet to calculate the E0 cell for the reaction, and this reaction is given, and explain how the value of E0 cell calculated predicts whether the reaction is not likely to occur. So if you look at this reaction, what's happening? Copper 2 plus, I is -1, okay? Copper is +1. So there's an electrode involved where you have copper 2 plus changing into copper 1 plus. So copper 2 plus plus 1 electron in equilibrium with copper 1 plus. We can look at the data booklet for a value for this. It's this one over here. Copper 2 plus electrons, and it's forming copper +1. It's 0.15 volts. So this is 0.15 volts. Okay, so I'm going to look at this equation, and I'm going to try and find out which two electrodes actually made up this equation. The other one is the oxidation part is I-1 is changing into I2. I2 is 0 and I is -1 over here. So that means the equation with iodine. Where's the equation with iodine? It's over here. I2 and I-1, and the value is 0.54 volts. So I'm going to write that down. I2 plus 2 electrons in equilibrium, and it's forming 2I-1, and the value is 0.54 volts. Now we need to find out what's happening. Copper 2 plus is changing into copper 1 plus. So this is what's happening. You can have a look over here. Copper 2 plus is changing into copper 1 plus. And I-1 is changing into I2. That means I-1 is going backward and changing into I2. So this is the reaction that's happening. And it shouldn't actually happen. I mean, this reaction is not feasible. Why? Because I2 is the equation that's the higher potential. Higher potential is the one that likes to actually gain electrons. So it should go in the forward direction. It shouldn't be going in the backward direction. So how did you calculate E0 cell? E0 cell was I mean, there were two formulas that I stated. One was that it's higher potential minus lower potential, or it's the reduction potential or reduction E naught minus the oxidation E naught. Okay, when we were studying electrochemistry, this is what I told you, that the proper term is reduction E naught minus oxidation E naught. Now over here, this reaction should not happen. Okay, because this is the higher potential, it should be gaining electrons. Okay, not not going from I minus 1 to I2, it should be going in the forward direction. Okay. Sarah, is this clear that this reaction should not happen? Abu Rera, Aisha, Akib?
Yes, sir.
Yes, sir.
Acha, so how do you calculate E naught cell? Normally you calculate E naught cell higher potential minus lower potential, but this reaction is happening completely the wrong way. So use the term reduction E naught minus oxidation E naught. Which one is getting reduced? The first one. So it's 0.15. And which is the oxidation part? This is getting oxidized in the reaction. So this is 0.54. So if you do the calculation, do the math, this would come out to be minus 0.39. It's going to come out to be minus 0.39 volts. Minus indicates, this minus voltage indicates that the reaction is actually not happening this way. Okay? Minus indicates that the current is actually flowing in the opposite direction. Okay? This is not what's supposed to happen. This should lose electrons, this should gain electrons, because this is the higher potential. So explain how the value of E naught cell calculated predicts that the reaction is not likely. So E naught cell is coming out to be less than 0. So that means that the reaction is not feasible. Okay, so remember this thing, that जल्दी में हमेशा क्या करते हैं कि we think that E naught cell is higher potential minus lower potential, except, and why do you think higher potential minus lower potential? Like over here, higher potential gains electrons, so it's the reduction potential. Lower potential loses electrons, so that's the oxidation potentials. So it's reduction minus the oxidation. So remember this, that the other way to think about higher and lower is reduction and oxidation. So over here, because the reaction was happening in the wrong way, so instead of using high E naught minus lower E naught, I did reduction E naught minus oxidation E naught. And I got a negative voltage, which indicated that the reaction and the electrons would not flow in the direction that you are actually thinking. It's going to go in the opposite direction. As the next one is, in an experiment, a solution of I minus 1 aqueous is added to a solution of copper 2 plus. A reaction does occur in a precipitate of sparingly soluble copper I. So he's saying in reality, or in an experiment, I think, he's saying that a reaction, I mean, what's the reaction? He's saying I minus 1. So there's I minus 1 and there's copper 2 plus aqueous. And he's saying that the reaction does occur. I mean, it shouldn't occur, but it does occur. And a precipitate of sparingly soluble copper I solid is formed. The concentration of copper 2 plus remaining in the solution is 1 mole per dm cube, and the concentration of copper plus 1 in a saturated solution of copper I is 1.3 times 10 per minus 6 mole per dm cube. Use the Nernst equation to calculate the electrode potential E for the copper. So we need to, so basically this was all just a story that they had written. You just have to use the Nernst equation. What is the Nernst equation? It's E naught. So it's E naught plus 0.059. Okay, that's how you, if it's a non-standard potential, if non-standard conditions are used, you use the Nernst equation. So it's log of oxidized species, its concentration divided by the reduced species. This electrode, the standard electrode we had written was copper 2 plus 1 electron and in equilibrium with copper 1 plus. And I think, what was the potential for this? The potential for this was 0.15 volts. So this was 0.15 volts, but standard potential. Now it's not going to be 0.15 volts because the concentration that he's using for copper 2 plus, he's using the standard concentration, which is 1 mole per dm cube. But for copper 1 plus, he's using a very low concentration, which is 1.3 times 10 per minus 6. mole per decimeter cube. Okay, now based on this, by just looking at this, the concentration of copper 1 plus is very, very low. So that means the equilibrium would actually shift in the forward direction. And if it shifts in the forward direction, the potential is going to be much higher. E would be greater than 0.15 volts. Okay, so the potential, the equilibrium should shift in the forward direction because the product concentration is very low and the reactant concentration is relatively very high. So the equilibrium would favor the lower concentration side. So this is what we have predicted according to Lee-Shatler principle. So now we're going to use the Nernst equation. So what's the new potential? E naught is the old potential, which is 0.15. 0.059. What is Z? Z is the number of electrons. How many electrons does the equation involve? That's 1 electron. Then you take log of oxide species. Which one is the oxide species? I told you that the left one is the oxide species in the equation in the data booklet. So that's 1 mole per dm cube. And which one is the reduced species? The right one, which is 1.3 times 10 power minus. It's 10 power minus 6. So using my calculator now, take just 1 second. You can try and solve this. So the value is going to be 0.15 plus 0.059. That's going to be multiplied by log of 1 divided by 1 divided by what? 1.3. E minus 6. And just 1 second, let me check the brackets. So I'm getting 0.497. So I'm getting 0.497 volts. That's the value that I'm getting. किसी ने check किया? Akib, did you check this calculation?
Yes, I did. It's 0.497. Can we round it to 0.5?
Just 1 second. Because you have to look at the significant figures that are being used. So the minimum significant figures that are being used is 2 over here, 1.3. So that's 2 significant figures. This is 3 significant figures. So your value should be rounded to the minimum.
0.50.
Okay, so it's going to be 0.50 volts. Okay. Asha, so remember the Nernst equation. Okay, equilibrium shifts to the right or left, the E naught value changes. The Nernst equation gives you the actual value. Can remember okay, oxide species is the left one and the reduced species is the right one. अच्छा खैर अगला वो कह रहा है कि copper 1 chloride is also sparingly soluble in water. Suggest why the following reaction does not occur. So copper 1 chloride. Achha, why is this reaction actually happening? Okay, I'm getting ये दो reactions थे ना. So we are actually getting 0.5 volts. ठीक है और मेरे ख्याल से probably he's using a higher concentration of I minus 1 ताकि 0.54 becomes lower. That's why probably the reaction is happening. If you increase the concentration of I minus 1, the value would actually drop. Let's say it drops to 0.45 volts. So if you use according to what he just stated, higher potential gains electrons, lower potential actually loses electrons. So the conditions that he had mentioned, in those conditions, this reaction would actually be feasible. And so why does this reaction not happen? Now, the reason for this is the only thing he's changing is instead of the iodine equation, ये clear है ना सारा आके अबू रहरा आयशा, is this clear?
Yes, sir.
ठीक है
Yes, sir.
क्योंकि Nernst equation using the Nernst equation, the value that we got was 0.5 volts, so that was much higher. So higher potential gains electrons, or he must have done something to make this slightly lower by increasing the I minus 1 concentration. So the reaction did actually happen, which was not feasible under standard conditions. So now he's saying, why does the reaction not happen even if you change conditions if chlorine is used? Now, if chlorine is used, remember, and let me rub this off. So instead of iodine, remember iodine is 0.5, around 0.5 volts. So if chlorine is used, chlorine in the data booklet has a potential of, it actually has a potential of a standard potential of 1.36 volts. So that's really, really high. So that's, I mean, no matter what you do to the conditions, you can't make it the lower potential because the difference is huge. Iodine wali ke andar or copper wali ke andar, the difference in potential wasn't that much. So by just altering the conditions, you could actually bring this value up and this value down. But with chlorine, that would be kind of impossible because chlorine's potential is really, really high. It's very high, and it's always going to try and gain electrons. Not, it will not try to lose electrons, okay? Because it's a very high potential. So Cl minus one would actually be changing into. So suggest why the following reaction does not occur. Actually, इसमें यहाँ पे मैं एक सेकंड कर भी लेते हैं. And Cl2 plus 2 electrons. To Cl minus 1. ठीक है, this is right, yes. This is 1.36 volts, this is 0.15 volts. So there's a huge difference in the potentials. So higher potential gains electrons. So this would go in the forward direction. So it would actually be, there's a huge difference in the potential values. So no matter what you do to the conditions, the potential values, the higher would not become the lower, and the lower would not become the higher because there's a huge difference between the values. So in this, it's Cl2 that's changing into Cl minus 1, not the other way around. It's not Cl minus 1 that's changing into Cl2. That's not possible. And it's going to be copper 2 plus that would be changing into, sorry, copper 1 plus that would be changing into copper 2 plus. तो बस इसका आंसर लिख लूं. So not going to go back, ठीक है? So I think we'll continue with this in the next class then, ठीक है?
Okay, sir. Allah Hafiz.
Okay, Allah Hafiz.
Allah Hafiz.
Allah Hafiz.